Good morning. Welcome back. Today we'd like to talk about conditional probability and Bayes' theorem. It sounds scary at first, like lots of things in probability do. But the more that we work with Bayes' theorem and conditional probability, the more that we see that they're actually really useful tools for helping us understand how to slice up that sample space. When we were working with Venn diagrams before, we saw that the Venn diagrams helped us partition some universe set or sample space into smaller groups. Well, conditional probability will help us do the same. And even more, they'll help us only focus on part of that sample space. That is, in a Venn diagram where I might have had two groups, and I could have given you the probability that I would appear in that group, that was great. But really, if I was more concerned about, well, I already know I'm in one of the groups, so if I'm already in one of the groups, what's the probability that I'm in both of the groups? Right? So those kinds of things were a little bit harder to get at with our blank out of blank, right? A notation for probability. And we can still do it though, right? I've given a table here on my first slide. We can still look at this. For example, I've given a table form of a Venn diagram here, and I've asked to calculate the probability of A intersection B. That's this here, probability of A intersection B. Well, those are the ones that are in both groups at the same time. So looking at my table, it appears that there are 10 in both groups at the same time. That's the group here in both A and B at the same time. And how many is that out of? That is out of a total of 70. And that's the grand total down here at the bottom. 10 out of 70 gives me a probability of 1 over 7 if I reduce that fraction. That wasn't super crazy. Let's see, let's look at the probability that I'm in group A. Well, group A is split up into several different subgroups, the 10 and the 25. Here in the table, we actually have a total row that we did not have when we were doing Venn diagrams. So the table is actually a little bit more useful than the Venn diagram for this question. There are 35 total in group A out of a total of 70 total. 35 over 70 reduces to 1/2. And one more for good measure. The probability that we are in B complement or not in group B. Again, this is something in the Venn diagram may have been a little harder to see, right? Count all the places. But in the table, I've already got that. I've already got a total row for that. 30 out of 70. Which reduces to 3 over 7. So those were, I would call them the older methods of calculating probabilities. I was looking at the entire sample space, the entire group by default. And that's why the out of was always 70 for these three first probability assignments. But it won't necessarily be that way for conditional probability. They let me change the out of to see a little bit deeper. Before I go on, I'll remind myself from the last slide, the probability of A was 35 over 70, was 1/2, and I'm going to need that probability going forward. So if I assume that B has already happened, or I already know that I'm in group B, then what is the probability of also being in group A? The way I would write that is like this. What is the probability of A given that, or assuming I already know that I'm in group B? Okay, that's a vertical bar, and that's my symbol for conditional probability. So that says, what's the probability of A given that I'm already in group B? Well, if I'm in group A and I'm already in group B, then I must need to know this probability, the one that we talked about before, the A complement B. And now it's not out of 70 anymore. I am limiting myself to only looking at the people that are in group B. Well, that's the probability of group B. Okay, so I've changed the out of, quote unquote. And this is the formula, by the way. I'll copy it down on the next line. And this is the formula for how I calculate conditional probability. From the table, oops, sorry, I'll go back up here. No, that was correct. I thought I changed the numbers, but I did not. The probability of A intersection B was 1 over 7. If I remember from the last slide, that was 10 over 70 in my table. The probability of B, and that one wasn't given to me, or I didn't calculate it on the last slide. From the table, it is 40 over 70, 40 over 70, or 4 over 7. Reduce. 1 over 7 divided by 4 over 7 is 1 over 4. And the reason I was able to do that so quickly is I essentially multiplied by 7 on the top, multiplied by 7 on the bottom, canceled out both fractions. Whenever we're doing probability calculations, there are many times we actually prefer to keep our fractions unsimplified for a while because we know that when they're unsimplified, they're easier to get everything canceled out. It's better to have common denominators while you're still working than it is to have simplified fractions before you're ready to have a final answer. It's the probability of A given B is 1 out of 4. Another way that I can look at that is the given B part of conditional says limit your focus to only this possibility. Right? If I'm only allowing myself to be in this green box, then the people that are in group A are 10 out of 40, or 1 over 4. That seems a lot easier. Right? If I have the big table, of course, I can calculate this, right, with the intersection probability divided by that probability of B. But I think it's a little bit more intuitive if you say, in this green box, the probability of A is 10 out of 40. And that's only allowing myself to stay within the green box. If I opened it up, then it would be that intersection divided by probability of B. And that's the formula. I'll copy it down here again. To find the conditional probability, I find the intersection probability divided by the prior probability of B. Now, sometimes that probability will not always be super easy to calculate. We'll see a couple of examples today where we need to go roundabout to calculate that probability of B. But essentially, that's it. And just saying, well, find out what we want and the relevant total, the relevant out of blank in my table. And for funsies, before we move on, let's calculate the probability of B given A. I'll have to do it a little bit smaller. I didn't plan on adding another one here. That's all right. So using my formula, that is probability B intersection A divided by probability A. That's basically who are in both out of the A group. So we know probability of B given A is 1 over 7. We've used that several times. But now the probability of A was 1/2. 1 over 7 divided by 1 over 2, 2 over 7. And we might need our calculators to do that. Essentially, I'm multiplying times 2 and times 7, which would cancel both of the fractions. It would leave a 2 on the top, and it would leave a 7 on the bottom. 2 over 7. Notice how these two aren't the same. The conditional probabilities aren't the same. Probability A given B was 1 over 4. But probability B given A was 2 over 7. And the reason they were different, right, even though they still, the top number essentially was still 10, was that the second time, if I'm given A, I'm limiting myself to this box. Probability of B given A is 10 over 35. Whereas up above, the probability of A given B was 10 over 40. So essentially, they let me slice up my sample space a little bit more finely, because I'm only concerned about certain subgroups. That's what conditional probability helps me do. Let's look at an example. This one's from the homework. I believe it is number 1 or very close to number 1. I'll zoom in a little bit while I'm reading so you can see. Victoria buys a bag of chocolate chip cookies, which contains 8 chocolate chip cookies, 6 peanut butter cookies, 6 sugar cookies, and 7 oatmeal raisin cookies. What is the probability that Victoria randomly selects an oatmeal raisin cookie from the bag, eats it, then randomly selects another oatmeal raisin cookie? All right. So at first glance, this seems like we might need a super complicated tree to solve this. And we do need a tree. But since the only thing that we're really concerned about is oatmeal raisin cookies, I don't think I want to draw a tree which has all the possibilities. Okay? Chocolate chip, peanut butter, sugar cookie, oatmeal raisin. If I'm only asking you about oatmeal raisin cookies, why don't I simplify my tree to say either I get an oatmeal raisin cookie or I don't get an oatmeal raisin cookie? Right? I basically do the complement rule. That was essentially an expression of the rule from last week that we can do the 1 minus, calculate the probability of the complement. So it'll help me simplify my tree. And just to make things a little bit easier, because OR, I just realized looks like the word or, I'm just going to do R, raisin cookie, and not raisin cookie. All right. So this tree would represent the first selection from the bag. About that. The probability that Victoria grabs a raisin cookie the very first time in the bag is 7, because that's how many there are, out of, there are a total of 6 plus 8 plus 7 cookies in the bag. That's 12, 8 is 20, 27 total. 7 out of 27. I'm going to leave that as a fraction for a while. I know I could make that into a decimal or a fraction, or a decimal or a percentage, but over 27s don't cleanly turn into decimals, so I'm just going to leave that as a fraction for a while. So if there's 7 oatmeal raisin cookies in the bag, that must mean there are 20 not oatmeal raisin cookies in the bag, essentially 1 minus 7 over 27, 20 over 27. And this is the first cookie. That's the tree, represents the first selection. But again, that's not what we're really concerned about. So let me look at the second selection. This is where the conditional probability comes in. Because now, when I draw trees and I have more nodes than just the first one, now if I do the same thing and I do raisin cookie and not raisin cookie, this probability is the probability that I get a raisin cookie on the second draw, given that I have already drawn a raisin cookie on the first draw. And I might call that R2 and R1. What's the probability that I get the raisin cookie on the second draw, given that I've already drawn out one of the raisin cookies for my first draw? Well, that one's a little bit different now, because after I've drawn out the raisin cookie for the first time, there are no longer 27 cookies in the bag, and 7 of them are no longer raisin cookies, because I got one the first time. After the first draw, there are only 6 raisin cookies left out of 26. That's 1 fewer raisin cookie and 1 fewer total cookie. And the complement of that event, R2 complement, that means there are 20 out of 26 not raisin cookies in this bag. Essentially, 6 plus 20 gives me that 1. I know that my probabilities should always add up to 1 from any given node in my tree. That's the great part about using probabilities instead of counting, is that probabilities help us check our answer at every step along the way. Now let's see here. This probability would be the probability of getting a raisin cookie on the second try, given that I did not get a raisin cookie on the first try. Let's see, if I did not get a raisin cookie on the first try, that means I took a cookie out of the bag. That's an over 26, because I took a cookie out of the bag, but there are still 7 raisin cookies in the bag, because I didn't get one of them the first time. 7 over 26. Doing my 1 minus to give me the complement. 26 minus 7 is 19 over 26. Yeah, so the trees are full of conditional probabilities. I could even label these other probabilities. This one here is the probability of R2 complement given R1. This one is the probability of R2 complement given R1 complement. And so basically everything in the second layer of the tree and thereafter is a conditional probability. And I wouldn't ask you to do a third layer of the tree, but if I did, right, if I kept going, those would be conditional on the choice that you made for R1 and the choice that you made for R2. Right? Those are a little bit more complicated. We won't do a whole lot of those in this class. Let's get back to the relevant question. We wanted to know what's the probability that I selected a raisin cookie on the first try, ate it, and then get another raisin cookie on the second try. I think that is this path in my tree. Raisin cookie on the first try, raisin cookie on the second try. So I have highlighted the relevant path in my tree. What's the probability that I get this path in my tree? Well, I get raisin cookie first try and raisin cookie second try, so I should multiply those two fractions together. 6 over 27 times, or 7 over 27 times 6 over 26 is 42 over 702. And so the total probability here, 7 over 27 times 6 over 26. And if you wanted to do a little bit of reducing beforehand, the 6 and the 26 are divisible by 2. 3 over 13. So that is 21 over 27 times 13. 27 times 13 is 351 as a reduced fraction. And as a decimal, 27 over 351 is 0.076. I'll make it 0.77 to round up 3 decimal places. So that's about a 7.7% chance or probability or likelihood that this event will occur. Not super likely, but not completely unlikely either. 7.7 is a very small but still existent chance that this could happen. 21 over 351 would be the exact fraction. Interesting. Now for this problem, we didn't need to calculate all of the other probabilities. This is just the final probability for this one outcome. But I could multiply and find the final probabilities for all 4 of the outcomes. And if I did that, I would be able to add those 4 probabilities together to get a 1. Right? Starting from any node, tracing out all the possibilities, you will always get a 1. That's, again, the great part about conditional probability and probabilities in general. But I just did this 1 because the question only asked me about this one circumstance, or this one possibility. But when we're working with trees, we don't always get our way. In some sense, sometimes the questions that we ask can't be answered from the tree directly. There are lots of questions that can be answered from this tree directly. For example, if I wanted to ask, what is the probability that A occurs, period, that probability is already listed in my table. This is the probability of A. If I wanted to know the probability of A complement, that is also listed directly in my tree, A complement. If I wanted to know the probability of B, then things start to get a little more complicated. Because I can arrive at B in 2 different ways. Do you see how I could arrive at B through this path, the upper path, or I could arrive at B through the lower path? And I'll actually need to take both of those into consideration. Let's see what the table tells me. This is the probability of B given A, that I've already gone through A. This is the probability of B given A complement. This is the probability that I got to B, but I went through A complement. Same thing on the other side. I've got probability of B complement given A, and probability of B complement given A complement. So this tells me quite a bit about the conditional probabilities. And those multiply probabilities that we had at the end, I could calculate them. That would be the probability of A and B. That would be the multiply probability. This would be the probability of A and B complement. This one would be the probability of A complement and B. And this one is the probability of A complement and B complement. And if you recognize these 4 probabilities, they are the same 4 probabilities that occurred in a Venn diagram. So this tree is yet another representation of the same information that a Venn diagram could tell me. It's just that in the tree version of the form, I see conditional probabilities. I didn't see conditional probabilities directly in the Venn diagram, and I didn't see them directly in the table either. And so anytime I'm thinking about conditional probabilities, sometimes a tree is an easier way to express those probabilities. Let's calculate a few probabilities here. So the probability of B. We said before that probability needs to be broken down into several possibilities. That is, this probability, the top path, and this probability, the lower path. So that would be the probability of A and B plus the probability of A and, or A complement, and B. This gives me the 2 paths through the tree. Now, to calculate each one of those probabilities through the tree, I need to multiply 2/5 times 1/2 plus 3/5 times 3/4. We could type all this into our calculator to help us. This is essentially 2 over 10 plus 9 over 20. 5 times 4 is 20. 2 over 10 plus 9 over 20 is 13 over 20. But again, if you had your calculator handy, type it all in, and you don't have to do these fraction calculations manually like I'm doing. 13 over 20. I had to get that from doing it twice in my table. But notice that that's still just a probability of B. This doesn't really have conditionals as part of it, other than the multiplying that we did in the tree. What if I wanted to do the probability of A given B? Sorry about that. I scrolled down a little bit because I ran out of room on the slide up above, and I didn't want to clutter it so much. What I did was I copied the tree down below. The question that was on the table was, what if I wanted the probability of A given B? That's not a probability that's in my table. Remember, the conditional probabilities that we saw on the second layer of my table were always probability based on A or A prime, or A complement, because in my table, A happened before B, quote unquote. And that was the first layer of the table. The tree was A. So all the conditional probabilities in this tree were either conditional on A or A complement. But that's not the question that I've got in front of me. I want a conditional on B. And that's not something that I can read directly from the table. Let me go back and get my formula. So I know this means the intersection divided by probability of B. And lucky for us, we've already calculated probability of B. Right? When you're doing your homework, you may have to realize that you'll have to go back and calculate probability B manually, just like we did up above, right? And split that probability B out over several paths in the tree. But I kind of knew this was coming, and I went ahead and I calculated probability B beforehand, so I can just plug that in. Now, probability of A intersection B in my table is basically one path, A intersection B. That's where A happens and B happens. Okay, so that's a bit easier now. So that would be 2 over 5 times 1 over 2 divided by probability B, 13 over 20. And what sometimes I see students do, because they don't want to do this as two different steps. They'd rather say, "Professor, can I do all that in one step?" Absolutely. I would say, well, you've identified the path that leads to the result you want, but on the bottom of the fraction, you also have to include the path or paths multiple that lead to the same prior result. Right? Do you see how there's more ways to get to B here? Essentially, this is how I calculated probability B up above. So you don't have to do it this way with a big giant fraction with a bunch of possibilities in the bottom. You could say, I've already done that. I'll do it separately. That is 13 over 20. I don't need to see all that again. And so you might say, well, let's see, that is 2 over 10 divided by 13 over 20. I'll ask my calculator what 2 over 10 divided by 13 over 20 is. but I think it is 4 over 13. You can check me on that. I just did it in my head. I multiplied times 20 on the top and on the bottom. Cancels on the bottom, but on the top, and it wouldn't fully cancel. 2 over 10 is the same as 4 over 20. So then it's 4 over 13. That is the probability that I'm looking for. The probability of A given B is 4 over 13. It's a little bit tougher to do out of a tree that's not set up for given B type probabilities, but that's okay. We see this quite often, actually. So the Bayes theorem just helps us sort all this out, sort out the conditional probabilities, and give us all of the different possibilities. Matter of fact, I can give you the formal statement of Bayes' theorem. Sometimes complicated ideas can come in very small packages. You can see in this formal statement of Bayes' theorem that basically I can turn around the conditional probability this way. But I have to also know what probability A is and probability B is. Sometimes we have to go dig through it to find, right? So very often this denominator part will come to us, right, in this form. The probability of B given A plus the probability of B given A complement. Or maybe even more, right? If your tree was more complicated, you might need 3 or 4 or 5 probabilities on the bottom of that fraction to accurately capture all of the different possibilities. Okay? You might be able to imagine a tree which has many different possibilities, and you would have to snake through them and say, okay, this is the one I want, but there's other ways to get to that B probability. You would have to find all of them in the table. There might be many different ones on the bottom of that fraction. So that's kind of interesting. Right? The Bayes theorem looks so simple when you write it as that single fraction, just like that. But because our trees are not usually set up in this way, we'll have to do the legwork and find all the different possibilities. I've given the informal definition of Bayes' theorem as well below. Right? Basically, I think about Bayes' theorem as a way to help me reverse conditional probabilities. We just have to do the legwork to capture all of the possibilities that go with that. One more example before we go. Because again, I don't want to gloss over it. Bayes' theorem is not something that's super easy. Right? First time I saw Bayes' theorem, I was like, well, that's weird. Right? Why does it work that way? It wasn't until I practiced for a while that it started to make sense. It started to say, oh, I get it now. You just do this, and we can look at it this way. We got to practice. So let's do a little bit of practicing together. Let's see, shooting free throws. Basketball player makes her first free throw. Okay, so here we're given a conditional on the first time. So we're making 2 free throws. The first free throw, we'll call it F1, an F1 complement. Do you make the first free throw or not? We are not given those probabilities that it looks like. But we are given that she makes the first free throw, there's an 85% chance that she makes the second. Given that you make the first one, there's an 85% chance that you make the second. And that's the conditional probability, right? That's conditional on you making the first one, the probability that you also make the second one. That's why we set up the tree this way. Right? And because I'm given these conditional probabilities, it would be really hard to express this same information directly in a Venn diagram or a table. A tree is really the right sort of diagram to make here because I'm given conditional probabilities. It says if she misses the first free throw, there's only a 60% chance that she makes the second. Oh, must have gotten in her head that she missed that first one. 60% chance she makes the second. Suppose that the chance she makes her first free throw is 55%. Oh, okay, so it does give us this information. What is the probability that, and then we've laid out several possible answers here. Let me fill out my table or my tree first before I continue. Well, if she makes the first free throw 55%, that must mean that there's a 45% chance that she doesn't make the first free throw. 45 over 100, but since we've already started with percentages, let's keep going with percentages. Well, in this first conditional, it should be an 85-15 split. Adds up to 100%. In the second, it should be a 60-40 split. In all of those situations, all I did was 1 minus. It's just that when I'm working with percentages, 1 minus is 100% minus. That gives me all of the relevant information from the tree. Let's see what it's asking about. What is the probability that she makes both free throws? Looking at my tree, that is this path. Okay, that's this path. So let's multiply. So that the probability that she makes both free throws, that's F1 and F2 intersection, is 55%. I'll go ahead and turn that into a decimal. Times 85%. Turn that into a decimal as well. And the nice part about the percentages is that they basically got the out of already captured as part of it, right? It's 55 out of 100. That's why it's 0.55. It's 85 out of 100. That's why it's 0.85. So the percentages take care of a lot of that for me. And it looks like there's no conditional or anything here that would cause me to sort of second guess myself on different ways that I could get to this outcome. So it looks like I'll just go to my calculator. What is 0.55 times 0.85? 0.55 times 0.85 is 0.4675. 4675. Again, you could give that as a reduced fraction, but 0.4675 should be an acceptable answer. A little bit less than 50%. A little bit less than a coin toss. Still pretty good odds. Let's see, what's the probability that she misses both of the free throws? Going back to my tree, we miss both of them. That's this path. Miss the first one, miss the second one. So that would be probability that I miss the first one, that's the complement, and I miss the second one, also complement. Following my tree, 45% times 40%, 45% times 40%, 0.45 times 0.40 is 0.18, or 18%. I believe we'll need to type that in as a decimal. You could type that in as a fraction. Again, 18 over 100, the same as 9 over 50, whichever way that you like to see these. So, not a great chance, right? But that's all right, because we don't want her to miss the free throws. We want her to make those free throws. Part C and part D, that's the more interesting ones. What's the probability that she makes exactly one of the free throws, okay? But not both of them? Let's go to the tree. So if she makes the first one, she misses the second one. So we want that one. And if she misses the first one, she makes the second one. We want that path. Okay. So that would be, I'll need to do this down below, part C. Probability that she makes the first one and misses the second one, or right, the probability that she misses the first one and makes the second one. So that's 0.55 times 0.15 plus 0.45 times 0.60. And again, this is just calculator work. I'm having to type it into my calculator in real time, just like you might be, because I don't come with all the answers kind of on purpose. I want to show you that it doesn't take a long time to do this, even if you have to do it all by hand or all with a very basic calculator. 0.55 times 0.15 plus, oh, I typed it into my calculator wrong. I did a plus where I should have done a times. 0.45 times 0.60. By the way, before I move on from that, my calculator told me 1.1325, and I knew that had to be wrong because 1.1325 was 113%. That's not the kind of, I don't expect a probability to be that high, right? Probability has to be somewhere between 0 and 1. And so I knew right away that my answer was wrong. Going back and doing this properly in my calculator told me 0.3525. The correct probability. It's about a 1 out of 3 chance. Right? A 1 out of 3 chance would be 0.3 repeating. So it's about 1 out of 3. So part D, what is the probability that she makes at least one of the free throws? So either one of these, right? Because she could make both. Okay, that's not out of the question. So at least one of them. Or this one. She misses the first and makes the second. The probability that she makes at least one of the free throws is these 3 paths. So I could do it just like I did part C, add together all 3 of these paths. But I see one little piece here that can help me. If I basically want all the paths except the last one, why don't I set up a 1 minus? Why don't I do 1 minus the probability that she misses both of the free throws? That's my way of saying I want everything except this last one. That's going to be much easier to calculate. 1 minus 0.45 times 0.40. Again, I'll go to the calculator. 1 minus 0.45 times 0.40. That should be 82% or 0.82. There we go. And again, the nice part is that at any point you could double check yourself to make sure that all of these probabilities do add up to 100%. You would have to keep all the decimal places if you did that, but that's okay. But just a little bit of calculation work. Like the hard part of this unit in general is not the actual calculations, right? Everything is just multiplying decimals, adding fractions, all things our calculators could do for us. Unlike Unit 3, for example, where they remember all the simplex stuff we had to do. We had to remember the entering and exiting and basics and non-basics. And that stuff was, I think, more complicated because of all of that conceptual. Now, this is still conceptual, right? We still had to make this tree. We still had to read this tree. So it's not perfect. I'm not saying if you thought Unit 3 was easy and this unit is hard, that you're crazy, right? There's still complicated stuff here, but it's a different kind of complicated stuff. I think it leads to easier calculations, and after you practice it a few times, I think it's a little bit easier to work with. And so that's basically conditional probability and Bayes' theorem in a nutshell. Right? I know we can get a lot more complicated. Hopefully in this class we won't have to do anything super complicated. We'll do another video on random variables, hopefully later today. See you then.